Section 9.9, Efficiency. In your textbook, this is section 8.8. Now, we've noticed before that if you have friction, you're usually going to have heat. If you rub your hands together, you're going to find that they get warmer, they get hot. What's happening is that some of the energy is being converted into atomic kinetic energy. So the molecules are speeding up, and as they speed up, it shows itself as the temperature rising. So when the molecules, say in a gas, are bumping off of the walls faster and harder than they did a minute ago, the temperature has gone up as a result. Now, it feels like the temperature goes up and it makes the gas move. But in either way you look at it, when you have faster moving molecules, you have a higher temperature. So if you have a machine, you cannot have a perfectly efficient machine, meaning you can't go perfectly from kinetic energy to potential energy or potential energy to kinetic energy. When a roller coaster starts at the top of the first hill and starts moving down, it gains kinetic energy, but it's also moving its wheels on the track. And that increases the molecular kinetic energy of the track molecules and of the wheel molecules and around the axle and those molecules. And everything is warming up. That's why that you would need to have grease on the axles, because it prevents friction, and that friction will increase the heat. So for that reason, you can't perfectly go from one form of energy to the other. You're always losing some. And that's called efficiency. How much energy can you transfer from one to the next? That would be a higher efficiency. If more and more is lost in heat, that would be a lower efficiency. So efficiency deals with how well one conversion happens to another. So when you consider one of the machines that we looked at, a block and tackle or a lever, these are considered ideal machines. So if the lever arm is twice as long, and the output arm is short and the input arm is long, that what you make up for in distance, it comes out as force. So you put a little bit of force in and you get a lot of a force out. That's the problem. You're never going to get a perfectly efficient. You're never going to get a mechanical advantage of 2 or 3 or 4 or whatever that machine is going to give you, because some of it's going to be drained away as heat. So for a formula here, the efficiency formula is that the useful work output, what actually comes out, divided by the total work input, how much you actually put in, is what you call efficiency. So if you put in so many joules of work, say 10 joules of work, and you get exactly 10 joules of work out, then you have a perfectly efficient machine. Problem is, in this world, there are no perfectly efficient machines, because all machines, as you use them in order to multiply your force, you're going to end up leaching some of it away as heat. So let's put some numbers here. If you put 100 joules of work onto a lever and get 98 joules of work out, then the lever is 98% efficient. So 2% of it is lost with the fulcrum grinding against the bar, and that is what is going to cost you the efficiency. 98% would be a tremendous efficient machine. When you're talking about heaters are very inefficient, as we'll look at in a minute. The next example, in a pulley system, a larger fraction of input energy is lost as heat, because you end up with more and more axles, because the more pulleys that you have, the higher the mechanical advantage can be, but each of those pulleys have rope twisted around them in more than one place, going around circles. All of those circles have axles, all those axles grind on each other, and all those parts grinding with other parts are all going to have friction force, which creates heat. So, for example, if you do 100 joules of work and the friction of the pulleys dissipates 40 joules, then your work output that you actually get is 60 joules divided by the 100 that you put in it, it's a 60% efficient machine. 40% has been lost as heat. Let's look at another machine that we haven't seen before. An inclined plane is a machine. So if you were to have, say, a step, and you have to lift a big box up that step, you have to hoist it directly up and then onto the step. That may be very difficult. If you put instead a ramp, which is an inclined plane, then you could push that box up the ramp. Now it's going to take a longer distance. The step is shorter, the ramp is longer, but the force that you put on it is less. Okay, so here's the problem. You've got more friction as you push a box across a longer distance on an inclined plane than you do to simply hoist it up through the air. It just takes a lot more strength. If you're going to lift a refrigerator up a step, that's a lot of effort. If you use an inclined plane, which by the way could even be a wheel, then you are making it much easier to lift it up the step, but you've got a wheel grinding on a wheel, or you've got a box sliding on an inclined plane, and there's friction everywhere, and it's draining off some of your energy. So here's an example. Pushing a block of ice 5 times further up the incline than the vertical distance is lifted requires only a fifth of the weight. Okay, so if you were to lift it up a meter, you would have, however many newtons that ice weighs times a meter. Well, if you push it 5 meters, okay, remember it's force times distance, you're lifting it the same amount because it's at the end it's the same. It doesn't take as much. It would only take 1/5 of that. That is the theoretical mechanical advantage. That's what the paper says you could do, or your book says you could do. The theory behind it is just on paper, but if you're actually pushing ice up a block, I guess it would depend on a lot of factors: temperature, what the ramp is made out of, every imaginable thing. You might only it might take more or less than you figured on paper. An icy plank used to slide a block up the same height might have an efficiency of almost 100% because ice has a very low friction. So especially if you had something highly polished and then you were sliding ice, or if you were sliding like dry ice that was actually putting gas down on the surface and floating on the gas, then it would have a very low friction and you could have almost 100% efficiency. But if you have any microscopic ridges, you would have a lower and lower and lower efficiency. So friction requires you to exert more force, and more force is going to, it decreases the work output that you're going to end up with. So here's the efficiency. Your actual mechanical advantage, how much that it actually helped you, divided by your theoretical advantage, is efficiency. Normally it's presented in a percent, so you would have actual mechanical advantage over theoretical mechanical advantage times 100%, and you would say that the efficiency is 89% or 35% or something like that. Efficiency is always going to be a ratio or a fraction less than 1, and then when you multiply it by 100%, you'll end up with a percentage less than 100%. Here's another machine that we haven't looked at. These are called complex machines. This auto jack is an inclined plane wrapped around a cylinder. Now see if you can see it. Let's imagine that jack is actually a building, and you can walk around and around and around all the way up to the top of the building. Essentially, instead of taking a step, you're just going longer distance, but it's easier. There's a science building that I know of in Pittsburgh where it was built in the 1920s for huge physics equipment that would weigh very, very heavy physics equipment. There were no elevators at the time. I think it was actually 1800s. There were no elevators installed at the time, so what they did is all of the hallways had long ramps that would go up from one floor to the next, and it took the entire distance of the building, so it was a very, very shallow ramp, and you could go You could pull with a hoist or with a block and tackle or push things up the ramp relatively easy, much easier than hoisting them straight up from one floor to the next. So essentially, a complex machine like this, an auto jack, is just a disguised inclined plane that wraps around. A screw will behave the same way. A single turn of the handle raises the load a very small distance. So you're putting a lot into it, 16 centimeters around, but it's only going up 2 millimeters. Okay, so it takes a long distance to go up, but it's much easier to turn that handle than to lift your car with your hand. So if you have the distance for the circle of the handle 500 times bigger than the distance between the ridges, the theoretical mechanical advantage is 500. It should be 500 times easier to use a jack than to lift the car. The problem is, since it's going up 2 millimeters at a time, all of that is sliding on that jack, is sliding on those little ridges. That's lots of friction. That's more and more friction. So the efficiency might be only about 20%. You might be wasting 80% of it just in heat. But if 20% of lifting a car is still easier than lifting the car with your hands, or if you couldn't lift a car with your hands, you would go for it. Okay? So the jack actually multiplies the force by about 100 times, so the mechanical advantage is 100. So if the efficiency of it is only 20%, then instead of 500 mechanical advantage, 20% of 500 is 100, and you would only get 100%, or a mechanical advantage of 100 times easier. That's still pretty good. So this is chemical energy. If you were to have, say, gasoline, so the gasoline, you've got a chemical reaction going on, and you're turning it into heat. Is that efficient? Is that an efficient way of making a motor run by heating up something? Okay, well, let's see. Turns out that even the best designed gas-powered automobile engines are unlikely to be more than 35% efficient. Almost all of the energy from the gasoline is going into heat. That's why your engine is so hot that you need a cooling system, like a chamber that actually cools down the engine, because that engine essentially are little explosions of burning gasoline, and that is mostly heat. That's why you would burn firewood, because you're trying to get heat out of it. Well, if you're burning gasoline, if you've ever seen gas burn, it burns ferociously. You're getting most of it wasting in its heat. Same thing with a light bulb. If you have a normal light bulb, you're getting more heat out of that light bulb than you are light. So a light bulb is very inefficient, and that's why like an LED would be more efficient. Okay, let's see if you remember anything. If you pull a sled, okay, with a total weight, a child in a sled, total weight of 500 newtons, up 10-meter slope. Okay, so it's a long 10-meter inclined plane that goes up 1 meter of vertical distance. So it would be, something like this, going up 1 meter. And they're pulling the kid up the sled. What's the theoretical mechanical advantage? Right? So remember, the theoretical mechanical advantage is you have the input distance over the output distance, okay, and hoping that the input distance is much longer, because the longer the input distance, the smaller the force will be, because force times distance is work. So the longer you can make the distance, the shorter you can make the work, or the force. So the input distance is 10. That's how the sliding up is 10, but it's going up 1. So it's a 10 over 1. So that's a mechanical advantage of 10. All right, did you learn anything? Why can't a machine be 100% efficient? It's always going to have friction involved, and friction always causes heat because it grinds surfaces against surface, increases the kinetic energy of the molecules in that material, and as such will warm up the material and loses some of the energy. So your efficiency is going to be based upon how much that you can get out, based upon how much you can put in.